Good evening. I am Luca Sabatucci from Italy, from the National Research Council, and I'm the speaker of this work by the title MonteCarlo Research with Goal-Based Heuristics. The work is part of the development of a self-adaptive middleware in which the self-adaptation is obtained by on-the-fly planning and replanning of atomic services, and therefore the core of the algorithm is a planner that works in a deterministic domain with symbolic goals. In this domain, several alternative actions characterize the planning domain. Then, the tree-branching factor is typically I. Moreover, single action typically don't have a direct impact to the goal satisfaction, but sequence of multiple action typically produce observable results. As a consequence, the space contains a considerable number of similar states with respect to the goal satisfaction. Moreover, we prefer working without a domain utility function in order to make our self-adaptation general from the specific context. We adopted an approach based on MonteCarlo tree search because it combines the precisions of tree search with the generality of random sampling. Moreover, it also provides a simple way to handle local minima and plateau. The algorithm is composed with a blind exploration of the state space, which is driven by goals and their decomposition in subgoals, and in particular we use a measure of the partial satisfaction of these goals. As you surely know, the MonteCarlo tree search, the key idea of this algorithm is to evaluate each state of the space by using the average outcome of a number of simulations, where simulations are random walks from a specific state towards a terminal state that is typically a state in which the game, because Monte Carlo is typically used in games, the game is win or lost. And the outcome of this simulation is used to update the value of the explored states. Now we have a problem that is that when we use MonteCarlo tree search with predicate goals, there is a problem due to the fact that a few states propose a significant change in terms of goal satisfaction, and of course it's unlikely that simulation just terminate in one of these ideas. So our key idea is to use a simulation driven by a degree of partial satisfaction. Indeed, each node of the space has an ideal distance from the final state, from one of the exit states, but this is an ideal distance because we cannot, we don't know a priori this exit state, so we can only provide an estimation of this distance. And the estimation must be domain independent because we don't want to bind to a specific domain. Must be automatically derived from goals and subgoals, and efficiently computed in all the states of the space. To this aim, in some previous work, we propose a metric for measuring the partial degree of satisfaction that is an electrical metaphor. The idea is quite simple. If a goal is decomposed in sub-goals, the satisfaction of each of these sub-goals has a direct impact to the overall satisfaction. So, if we consider that this goal is satisfied, then it's like act like a closed circuit that leave the current pass through. Otherwise, it behaves like a resistor that opposes to the current. A logic hand, in this way, recall a series of resistors, and a logic OR recall a parallel OR resistor. In this figure, you can see a simple representation of a goal G and its equivalent electrical schema and the corresponding formula. So in paper you can find more details. The algorithm is a recursive algorithm that browses the formula and use four possible patterns to evaluate the resistance to satisfaction. Now it's time to move to the real focus of this paper, that is the R2S Monte Carlo. It is a modification of the classical Monte Carlo because for us a number of reasons. First of all, we use a token set to maintain a trace of the interesting nodes that we are going to find in the exploration. A root node is always in because we won't give a non-zero probability to restart from the root goal. Then the node selection is a random extraction from this token set. The simulation is driven by the metric that we've seen before, the R2S. Each new node that is explored by simulation is evaluated through the R2S, and the simulation terminates when discovering a new node in which the R2S changes. If the change is positive, so we improve the satisfaction of the goal, it is a delta node and it is added to the tree. Otherwise, it is simply skipped. The backpropagation step updates the token set according if we discovered a delta node or not. In figure, there is an example of the first iterations of the R2S Monte Carlo. The first iteration, the token set only contains the root node, so we select it, and in a simulation we find a delta node B8. It is added to the token set and also to the tree. In the second iteration, we restart again from V0, the root node, and we find another path, simulation path, but it terminates in a node that not improve the R2S, so it is not added to the tree. In the third iterations, this time the V8 node is selected for exploration and it conducts to a new delta node, V12, that is added to the tree, and so on. So, concluding, we used an experiment in the smart ship domain to provide some preliminary discussion of the algorithm. In this domain, we used the R2S Monte Carlo in order to planning power flows for supplying electrical components of a smart ship according to a specific mission and possible failures, electrical failures that occurred during the mission. So it is a combinatory problem because the planning algorithm must find a configuration by controlling switcher and electrical components of the ship. In this case, the branching factor was about 40. In this domain, we add an heuristic based on a utility function, and we used that as a benchmark for comparing our algorithm with other algorithms, and first of all, a best first exploration with this utility function. And we discovered that our algorithm performed as well as, on average, a best first plan with utility function, and that was a good result. Moreover, the R2S MonteCarlo performed good also in comparison with Monte Carlo that, without our R2S metric. Another interesting characteristic of this algorithm was that delta nodes help highlight a portion of the space that worth being explored first. So an interesting feature is an asymmetric tree growth that is specifically suitable for dealing with problem like those I presented with an high branching factor and in which actions must be composed in order to provide a result. This is all. If you have any question, please ask me or send me an email to the address.